Now that we've defined functions, let's talk about the next logical step, which is limits and continuity, both which are necessary for us to do calculus. So let's look at this definition. Let f be a function of two variables whose domain D includes points arbitrarily close to a, b. Then we can say that the limit of f of xy as xy approaches ab is L if for every epsilon greater than 0, there is a delta greater than 0 such that xy in the domain and 0 less than the square root of x minus a squared plus y minus b squared is less than delta, then the absolute value of f of xy minus L is less than epsilon. If this is so, we write the limit as xy approaches ab of f of xy is equal to L. Now, being able to actually calculate limits is very difficult in determining whether or not it's true. So most of our examples that we have is actually showing when the limit does not exist. A note, L'Hopital's rule, like when you have that indeterminate form, does not apply. That is only for the one-dimensional case. So let's see what I'm talking about in this next example. So we ask if this limit exists. Well, before, when we were talking about limits in one space, you could either approach on a timeline, on a number line, a point from two directions. You could either start here and travel to the x, or you could start here and travel to the x. But now we're having a y component. And there's not just one way to travel to this point. You could travel this way, or you could travel this way, or we could get crazy and travel this way, or you could travel this way. So many ways to travel. And that's the idea for testing the limit, because the limit will only exist if all of these paths, all these ways to travel, reach the same value. Maybe this will make more sense. So if I start with this limit, and I start with the limit as x approaches 0, and I already have y equaling 0. So I have x squared minus 0 squared over x squared plus 0 squared. Now, in this case, this would be like we are starting with y equals 0, and we're traveling this way along the path. Well, this would be just the same as the limit as x approaches 0 of x squared over x squared, which is equal to 1. But what if I did the same thing, but now I start with the limit as y goes to 0 with x being 0. So I'd have 0 squared minus y squared over 0 squared plus y squared. This would be as if I'm approaching along these axes, so going along the y-axis, right? Because the idea is I have, in this case, a fixed 0 and y is variable, where in the previous case, my x was variable and my 0 and my y was fixed. Well, in this case, I get the limit as y goes to 0 of negative y squared over y squared, which is negative 1. Well, does 1 equal negative 1? No. So we get two different values depending on which way we approach this point. So therefore, the limit does not exist. So let's look at this other limit, and let's do the same thing. So we start with our limit as x goes to 0 of, now it's 0, because y equals 0, of x squared plus 0 squared, which is just 0. All right, so that's pretty simple. So let's do y. Limit as y goes to 0 of, 0 over 0 squared plus y squared. Oh, that also equals 0. So does the limit exist? You may think yes, but remember, there's so many ways to approach. Let's think of it from a different perspective. Let's think of it now instead if we had approached from this point, right, this line right here, where x equals y. So instead, we would still have the limit as x goes to 0, but we would be having along the line x equals y, so we would be saying x squared over x squared plus x squared, which is the limit as x approaches 0 of x squared over 2x squared, which is just 1/2. 1/2 does not equal 0, so the limit does not exist. And this is because we're approaching, right? 0, 0 is on this line. So this line here shows it. Let's get even trickier. What if we had this limit here? Well, same sort of thing. Let's start off with x going to 0 and y equaling 0. So along that line. And we get 0 over x squared plus 0 to the 4th. Well, this is just equal to 0. Now I'm going to tell you, if you do x equals y along this line, you'll also get 0. We have to think of a different one to test again to see if it doesn't exist. Now, my intuition is we have y to the 4th up here. We have a y squared. So let's have x equal y squared. Now, if you think of x equals y squared, that's going to go through that point. So that is a curve, and that's an approach we could use. Not a straight line even. We're looking at a parabola now. So if we have from here x equals y squared, we're going to have the limit as y goes to 0 of x, well, y squared over y squared squared plus y to the 4th, which is just the limit as y goes to 0 of y to the 4th over 2y to the 4th, which is equal to 1/2. 1/2 doesn't equal 0. Bada bing, bada boom, the limit does not exist. Most examples we'll give you is going to be trying to show that the limit does not exist, because it's very difficult to show that the limit actually does exist. You'd have to use the definition that we've taught you there, or some other rules, which we'll talk about later. Therefore, I would just try to figure out what type of equation prevents this limit from existing. What type of curve, what type of approach do you need to take to prove that this limit might not exist?